So this week we will actually study and then do some experiment on buckling. Buckling is another one very important failure mode. And if you remember, what we discussed so far is that we usually go with sigma D and sigma actual, or tau D, tau actual, whatever, situation. And then we try to constrain the tau D or sigma actual with the design variables, design parameters. Okay, so this is basically the general approach for the design, general approach for the machine element design, or whichever that you need to solve for the engineering problem. That's the design procedure. However, if you have a chance to play with, say this is the, I think this is a good example. This one right here. If you had a chance to compress this, a beam like this, very slender beam, what's going to happen? This will be failed by this or something else. If I push it down, see what's happening. It's not compressed, right? It's not compressed by along the, for example, if sigma actual right here, in case of compression that I apply P on A, it has to be compressed, but this is not going to compress like this. What is this phenomenon? What do you call this? Huh? Anybody heard about this? Buckling, basically, right? So buckling is another important failure mode for a member just like this, very slender member. Okay, it's a slenderness ratio. We're going to talk about those ratio later on, but in case the length is much larger than the ratio between length and area, okay, it's something more than some threshold that you can think of this as what I call it, the column. In column, most common failure mode of column is buckling. And why the buckling is so dangerous? Once you start buckling, I can break it easily by applying just a little bit more force. I don't need a lot of force here to compress it, to break it. I just need a little bit more force, just break it. Okay, so it's easy for me to break. And then this is buckling is a very buckling is some phenomenon that's known to engineers that has to be treated in a different way. So we are not going to go through this, but there's some other process. So let's talk a little bit about buckling here. So in order to, I think you already learned about this, but I'm going to give you some refreshment of your memory. So in order to find the governing equation for the buckling, I'll say just GE, governing equation for buckling. Basically, we try to set up a governing equation to find out what we call PCR. Anybody remember PCR? What is PCR? Amount of the P, the force, that will start causing what? Buckling. So we call it a critical load. Okay? This is a critical load. So we try to find this guy here. That's our purpose. And we try to minimize, try to limit the force on the column like this below the PCR. Okay? That's our goal for the buckling. Okay? And then usually what we do is to go for PA, allowable, as a function of PCR over N. N is the safe factor. Just like this. It's similar to the approach like this, but what we will do for the buckling is that we find PA. Find PA. P below PCRs, which is P coming from PCR over N. So we try to find, we need to know PCR first. How do I find PCR? Well, there are some approach, but the easiest way is just to go with the physics, based on your physics. Physics is, again, try to set up an equation with some free body diagram of the phenomena, and find out the solution. Okay, that gives you some idea of what PCR is. So we'll just go for it really quick here. Before we actually do the find GE, which governing equation, I'll just make sure that there are some assumptions that we have to keep in mind. First, the column is straight. Second, it is elastic. And then third, it is P at the center. 4, P is vertical, not horizontal. And then number 5 is free rotation. So this is the some assumption you need to actually set up before you actually start setting up the governing equation. Okay. So this means that the force is acting right at center, not somewhere around here. Okay. Not this way, but center. Because if you bias the force a little bit with some eccentricity, it will cause further moment that basically will make the buckling much easier to cause buckling easier. Elastic meaning is sigma is equal to E epsilon. That's following this equation, and then P is and also the entire column is very straight. Is not crooked like this. If it is crooked, then again, this is easy for us to cause buckling also. So we try to deal with very standardized case, okay? Not the eccentrically crooked or eccentrically loaded case. And then P is a vertical piece. There's no force along the horizontal line. Free rotation meaning you have to assume that it is all pin joints, both ends, okay? Pin joints. So this is kind of our model to find out the governing equation for the buckling. Eventually, we'll find PCR for a given set of GE, the governing equation from our model. So the way we actually approach this, again, you apply force P right here, first of all. And I would like to set up a free body diagram to find out the governing equation. So the way we do is to sample this area and figure out the force right here. Reaction force should be equal to P, but at the same time, if it starts buckling like this, okay, buckling like this, there's a P right there at the center, P at the bottom right here. But also, because this force right here is not going to be aligned together, we're going to have to define the displacement along horizontal direction y. And then something else we have to define right here. What is it? To make this guy statically equilibrium, in its static equilibrium. There's something at the bottom right here. What is it? Moment. Just like the flat, this is the same as the pentagonal beam case, right? The only thing different is you apply force, the direction vertical to the beam, but here you apply the force same direction to the beam, member directions. That's the only difference. But if you do this, you have what? Direction moment right there. The same thing should be right here. What direction? What direction the moment has to be applied to make the guys in statically? Let's say you don't. First of all, just assume that m is counterclockwise, okay, positive, without knowing actual direction. But this is kind of a model that we can think of for a given column case, right? So I take it down. Separation is the first step, and then you draw all the force for the free body diagram, and then you set up an equation. How do I set up an equation here? Let's say this area, this location right there is x by x. So what I can do is to set up an equation for moment and sigma m at x is equal to 0, assuming counterclockwise positive. And then try to figure out the reaction force and actual force with respect to the geometric dimension. Okay, that's basically what I want to find out, because I want to find out the amount of deviation. Okay, and then eventually I'd like to evaluate this PCR later. Okay, so if I set up an equation of a moment equation right here, this is my reference point right here. Okay, then I can say, okay, m is a positive direction, m first of all, and what else? Anything else that might cause the moment? Huh? Moment. This p will cause moment or not? Huh? It's acting right through this reference point, so there's no moment right there by p. How about by this p? It causes moment or no? Yes, how much? P times y, right? P times y. Positive or negative? If I'm saying right here. P causes what? Positive. So positive P times what? Y is equal to 0. Very simple. Very simple. There's nothing else. All you have to do is just separate the part that you're interested in, and then you describe all the force and set up an equation. Either summation of the force is equal to 0 or moment is equal to 0. Okay? So this basically means that M is equal to P minus Py. P minus Py. Now, if you remember the deflection lecture, you may remember that the M over EI, what was M over EI? Anybody remember? As a function of deflection. This is basically deflection if you think about it. If you turn this to the, for example, by y, you basically deflect it because of the buckling, right? This basically starts causing buckling. And then if you remember the deflection, actually, the y amount, it has something to do with the M over EI. What was it? Remember this? D, y, d, x. Remember this? Second derivative. This is basically what we discussed last Monday, right? We're going to use the same equation, okay? Same equation to figure out the deflection y for a given moment of m, which is basically associated with the force that you apply, P. Okay? So this basically is again negative, because m is negative Py, it's Py over E. Okay? And what I'm gonna do is to just bring this to the left hand side. So second derivative of y with respect to x plus now P over EI, y is equal to 0. Okay? So what is this equation? What do you call this equation? Anybody took the differential equation of calculus 3 to, what do we call this?
Second order.
Ordinary, second order differential equation, right? Equation. Anybody know how to solve this? 1 point, 2 points extra. 3 points. This is calculus. How many of you took calculus? Raise your hand. So you should know how to solve it. You should know how to solve it. Maybe it's too long ago? Yeah. Okay. That's why I'm here to teach. But simply just all you have to do is to solve this equation. Okay. Then it will give you the amount of deviation y because of the buckling. Okay. Buckling. That's why basically what we are doing. We assume that it is in the buckling situation, and once it is buckling, we set up a geometry and then the force, and set up an equation with the static force equation and moment equation, and then we use the deflection and moment formula, which is very useful for a lot of different things. Okay, and this gives us the deflection equation. Okay, in second ordinary differential form, differential equation form. So let's just solve that equation really quick together, see how we find this PCR. So if you remember, in your early age of your university, D plus P, what was it? EI? Y is equal to 0, right? That equation, right? What I'm going to do is just simplify this guy here with some variable k. I'm going to use this in k squared. I think you have seen this before to solve this type of equation. So it should be the reason why we actually assume this in k squared is just for our convenience to solve it. Okay, to solve it. Nothing more than that. So mathematical trick. Okay, just a simple trick. So now if you look at this, I need to assume some type of possible solution for this equation. What type of function do you think will satisfy this type of second order ordinary equation, differential equation? This says that second derivative of your own function is going to be proportional to each other, right? A function, there's some function, a function that basically whose second derivative is going to be just what? Proportional to each other, proportional to its own function. What type of function could be, might have the property? So if you divide some function, what if I divide a function that has its own, keep its own function, shape of function? You know, no matter how many times you divide it will keep its own shape. What is it? It's too old? Too long ago? There is a function that seems like something like this. If you remember y is equal to ex, if what is the first derivative of this guy? Ex. Second derivative? Ex. Ex. It goes on like this. So one candidate for the solution of this type of function is going to be something like this. Okay? That's a good starting point. So with this, I can just, okay, dy squared dx, second derivative of y is going to be equal to, what is it now? R squared ex, correct? Because you have r, right? You just have to multiply something to the same, your own function. That's basically what it is. So you substitute this back into this equation, so see what happens. If I do this, it's r squared ex plus k squared e to the x, e to the x is equal to 0. Correct? Rx. Correct? That makes sense? So far so good? I didn't do anything. I just followed the way that people solve this ordinary differential equation. Now, if I see there are the common factor right there, e to the rx, so I'm going to take it out. This is equal to 0, right? So that means that maybe the first part right here in the parentheses has to be equal to 0, or this guy has to be equal to 0. To satisfy the multiplication of these two factors should be equal to 0. Which one should be equal to 0? What do you think? This will be 0? Only when x is equal to 0, right? But when x changes, you can't guarantee that e to the rx is 0 all the time. Correct? Meaning that this has to be equal to 0. That's the only way to satisfy this equation. So that means your r, what is your r then? Your r should be, the r should be 1, 9. Plus minus k, j, right? Complex number. That's the only solution that satisfies this equation, right? R squared plus k squared is equal to 0. That's the only way. So if this is okay, this means that your r is going to be, and we call this equation as a CE, characteristic equation, if you remember, okay? So this gives us some idea of what that r value should be. R value should be equal to plus minus k to the negative k to the kj, which is the complex number. Now, if r is complex number, the possible solution for y is going to be fixed to this: a sine kx plus b sine kx. Okay. Complex number basically will cause the function oscillate. I mean, if you took the vibration course, you probably know what happens. But the oscillation basically is usually described by the sine and cosine, combination of sine and cosine. Okay, so this is possible solution when it comes to the case that your r value is complex. Okay, I believe that you already took this a long time ago, but I'll just review this solution process. So I got this solution y, but am I done now? Done or not? Well, I know what was the k? K is right here, right? I define k just like this. But what was a? A is just constant number that basically coming from this equation solver. Solution actually is proposed like this, and I still don't know a and b. How do I find a and b? How do I find A and B? If you're stuck, what was it? Blue's Clue. Blue's Clue. What was the BC? What does the BC stand for? Boundary condition. Boundary condition. Okay. So let's think about boundary conditions. Say if I push and then I pause the buckling, and then if buckling happens, you might have a shape like this, right? You have a shape something like this. With a P. Okay, and then usually what happens if you see what happens here, if I push it down, this guy bulges, right? But usually it keeps its location of first and the last locations. It doesn't move like this, but it fixed along the vertical line, but it bulge. So that means that your y is not 0 when x is not 0. Y is, you have some y right here, right? Along the vertical line. But y at the starting location and then ending location should be always, huh? Always what? Y at x equals 0 and x equals L should be equal to always 0. It doesn't change. It always on vertical line. Right? Does it make sense? So that's our boundary conditions. That's your Blue's Clue. Okay, Blue's Clue. You need to use Blue's Clue whenever you're stuck or to solve an equation like this. So so then basically that means that we're almost done now. So that means, well, y when x is equal to 0 should be equal to 0, no matter what happens. And then y L when x is equal to L should be equal to 0. This is my Blue's Clue. Okay, Blue's Clue. So let's just try to apply this Blue's Clue to this equation to find out A and B. Okay, that gives us some good idea of how to find A and B. So let's just substitute 0 for x. So y 0 should be equal to, when x equals to 0, sign is what? 0. When, oh, I'm sorry, sine cosine. Why is sine? Nobody say I made a mistake. Maybe it was too long ago. Sine and cosine. Okay? It's a combination of sine and cosine. So when x equals 0, this whole thing is 0. When x equals 0, what is this? Cosine. Cosine 0 is 1. So that means b. Meaning b is equal to? B should be equal to 0. Because I said to b, blue said the when x equals 0, your y is equal to 0. If x equals 0, your y is equal to 0. That means b is 0. So that means your second term is gone. I don't need second term. All I need is first term, right? The first term, let's find out A. What is A then? Let's use the second Blue's Clue. So if I put L, y L is equal to L A sine K L. Right? A y L is equal to A sine K L is equal to, should be equal to what? 0. Now if this is 0, you may have to make A is equal to 0 or this guy is equal to 0. If A is equal to 0, what does that mean? The whole thing is 0. Whole thing is 0, meaning there's no buckling. There's no buckling. So it is trivial. It doesn't mean anything too much to us. So A should be 0, but this part has to be equal to 0, right? Sine. When sine is equal to 0, sine KL is equal to 0, so this guy has to be equal to 0, meaning this is the condition that for us to be able to find out the solution for this, so the equation. So when do you think your sine is equal to 0? Sine. I know when the parameter of cosine is 0, make the cosine 1, but when the sine function is going to be equal to 0? KL is equal to either pi, right? 2 pi, 3 pi. If you put any pi, Okay, multiplied by the integer value makes the sign 0. Okay, so that means your k, L is equal to some number n. I'm going to say n, some integer value n, and then pi. Okay, so k L is equal to n times pi. But what was k? What was k? K is k squared is p over ei. So k just the k is the square root of p over ei. That's your k times L, or L. Let's just bring L to the right. Is equal to n pi over L. Right? And I'm going to just square both sides. So this will give us, almost done now. This will give us P EI is equal to n squared pi squared L squared. Right? Okay, n squared pi squared L squared. And then I'll just take the EI to the right hand side, EI, get this guy out. So your P is basically a function of pi L EI. And this basically is the first possible